Hello. Today, we are going to talk about presentation, nuclear power. Is it really worse than choking to death in greenhouse gases? Obviously, the title tells you how I feel about the situation, so steel yourself accordingly. But I'll see if I can't make my case. We'll talk about the benefits and some of the drawbacks of nuclear power and see how they compare to other types of renewables and other types of fossil fuel power generation, and hopefully I'll change some minds. If not, well, at least you'll know what your opposition's thinking. So here's my bio. Obviously, I have a PhD in nuclear physics and a master's degree in nuclear astrophysics. I got out of grad school and I immediately went into teaching, and teaching didn't pay the bills like I would have liked. My first teaching position was 28 grand a year. And as I often say when I introduce myself, I like scotch, and it's kind of hard to get the scotch you like for $28,000 a year and pay off your debt from those 12 years you spent in college. So I very quickly changed careers and became a software developer. I also had a stint as a controls engineer, which was a lot of fun. I got to build machines for for factories and whatnot, conveyor systems, did some robotics. That was all great and fun, and now I'm sort of semi-retired and I'm back to being a college professor again. The point here, and the reason that I bring it up at the beginning of my talk, is that yes, I'm a nuclear physicist, but I'm no shill for the industry. I've never made the first dollar in nuclear power, or for that matter, nuclear physics in general. I had to change my career because there weren't a lot of job opportunities for me, and that's okay. I accepted that challenge and I did all right. But I don't really care one way or the other. I just feel like the debate needs to be an intelligent one, and it needs to be proffered by intelligent people. So I'm going to tell you my take on it, but remember that I'm no shill here. I don't have a dog in this fight. I don't have an axe to grind. And for that matter, even with global warming, I'll probably be dead before it's ever a problem for me, because I'm pushing 60 already. So we'll start by playing a little game I like to call Scary or Cool. Here you have a picture of the Challenger taking off and the cloud that it leaves behind it. You have a picture of clouds. Anything about either of these pictures scary to you, or is it just cool stuff? If so, here you have a nuclear power generation station and you have the same clouds coming off of it. Anything scary about that? Either way, I would say I don't know why either one of those things would be scary to anybody, because everything in all of those pictures is nothing more than water vapor. That is the big thing about nuclear power, is it does not put anything into the air that's not already in the air, like water vapor. And so when you start talking about the environment and greenhouse gases, nobody's going to want to move back into the cave and not have air conditioning and light anymore. But in the same token, nuclear power does not put carbon dioxide in the air while you generate that power. So that's kind of a big deal as far as I'm concerned. Here's another scary or cool game. Here you see fighter jets breaking the sound barrier. And again, that's water vapor coming out of the air because of the compression. But the thing that's cool about this is that's literally tracing out the sonic boom or the shock wave created by the fighter jet as it breaking the sound barrier. And so here's that eerie glow of that nuclear reactor, boy. That's scary looking, isn't it? Well, the funny thing about that is these are the same effect. So if you're not scared of the one thing, you have to ask yourself, should you really be scared of the other? And this is one thing I love to tell my physics class, even though it's not necessarily related to the material in the book. This is called Cherenkov radiation, that weird blue glow around reactors in their pools, in their cooling pools. That's called Cherenkov radiation. And what's happening here is you have high-speed electrons. They're going very close to the speed of light in vacuum, but they're in water. And light doesn't travel as fast in a media as it does in space or in a vacuum. So the charged particle, in this case the electron, is actually moving faster than light can move in that medium. And so what's happening is it's putting out a shock wave. The light that's being emitted by this thing going through this medium can't travel as fast as the thing that's generating the light itself. So the light comes off in this shock wave that goes off to the side, just like the sonic boom from a fighter jet. So we'll back up for a minute and we'll cover a few basics about radiation, because I laid this talk down yesterday and it only turned out to be about 30 minutes as far as what I really had to say. So I figured I'd go back and lay some basics for everybody to put that other 20 minutes in there, if nothing else. The first thing that we need to really drill home is, because it's like everybody knows it, but then they sort of forget it, is that radiation is natural. It occurs everywhere. It occurs all the time. And the reason radiation exists is because we're children of the stars. All of the stuff on the planet has come from supernovas that exploded, prior to the formation of the solar system. And so we have these heavy elements that are not stable, and they have certain half-lives. So you have uranium-238 that's naturally there. It decays to lead-206 through a series of alpha and beta decays. We'll talk about what an alpha and a beta and a little bit about what a gamma is as we go forward. But an alpha is just a helium atom, a helium nucleus. So it takes 4.5 billion years for half of the uranium-238 to decay away out of the Earth's crust and out of its mantle. Eventually, it goes through this chain, what's called a decay chain. It becomes thorium and palladium and, radium and radon. By the way, this is where radon gas comes from that might seep up in your house and might be a problem for you. So radon's always coming out of the soil because of this process. And eventually it decays down to lead, which is basically the largest of the stable atoms on the periodic table. So once it becomes lead, it stops doing this. But because the half-life of uranium is 4.5 billion years, you still got more than half of the stuff that we started with when the Earth was originally formed. Nuclear stability in and of itself, obviously, I think is a fascinating subject. I'm sure not everyone agrees with me, but a little bit of an understanding about nuclear stability and what you're seeing in this chart goes a long way to understanding nuclear power, chain reactions, and how all this stuff works. So what you have here is you have this graph that shows all the stable elements in the periodic table, as well as the isotopes, the elements that have extra neutrons that maybe aren't so stable. And so these are all the things that basically exist in nature or can be made in the lab and measured. The interesting thing about this are the black dots are obviously the stable elements that you would, hope to find anywhere. And this is not a straight line. If you were to project this out, the straight part of the line would go up here. So what's being plotted here is number of protons versus number of neutrons. And what you realize is that heavier atoms have to have more neutrons in them than they have to have protons. So it goes back to the nuclear force. It goes back to the fact that a large atom is always trying to sort of blow itself apart because those protons are always trying to repel each other electrostatically. And so the nuclear force has to be greater for every proton you have to hold a really large atom together, because the electrical part of it wants to try to blow it apart. And so as you go up in the periodic table, the bigger elements have to be neutron rich. And so this curve sort of lays over to favor more neutrons than protons. The other thing about this, of course, is that there is an optimal point. It is iron 56. That is the most tightly bound and most stable nucleus you've got. Anything smaller than iron 56 can be fusioned. It can be added two atoms together to make a bigger atom that's more tightly bound. And when you make something that's more tightly bound, you get energy out of it. That's fusion. That's a big promise for the future, but nobody's managed to make fusion work. So the other thing you can do is you can go up to the high end of the curve with this stuff that's already radioactive and this stuff that's already somewhat unstable from a certain point of view. And you can break it in half and you can move it down this curve, and you can make two more tightly bound nuclei that again will give off energy. Because the tighter that works in chemistry too. If you make a molecule that's more tightly bound than the molecules that came before it, then that's an exothermic reaction. That tight binding is going to lend itself to more kinetic energy or more heat after the reaction has occurred. So given that there's natural radiation out there, where does what's called ionizing radiation come from? That's radiation that's potentially damaging to the tissues in your body. And you see here from this chart that it is 84% natural and it is 16% artificial. So there's a lot of radiation out there. You live in a sea of radiation. You just maybe don't realize it. You take it for granted. And for that matter, we have evolved, and part of what drives the evolutionary process and what leads to evolution in the first place. But we have evolved to have an immune system that actually repairs damage from radiation. I was going to say something, the thought went right out of my head. Probably doesn't matter. I tell my students that all the time. It'll pop in my head later, and then I'll just randomly throw it out there. And then you'll go, why is he bringing that up now? That's not subject, but yeah. Such is life. That's how it works. So the 16% artificial radiation that you receive, most of that's medical. Most of that's going to the dentist and getting your teeth x-rayed, to make sure you don't have cavities or whatever, or some sort of x-ray, like if you think you have pneumonia and you have to go and get a chest x-ray. So 15% of what you get that's man-made is medical. And of course, the other thing that we've got to point out here is that as far as fallout nuclear discharges and whatnot, A-bombs, nuclear accidents such as Chernobyl and Fukushima, they account for 0.3% of all the background radiation you experienced. Oh, I remember what I was going to tell you about radiation, naturally occurring radiation in your immune system. There are actually models that show, it's called hormesis. There's actually models that demonstrate that a little bit of radiation is good for you because it spins up your immune system and it keeps your immune system going, sort of like an inoculation against a disease. So it's actually good to be exposed to a little bit of radiation. It makes you healthier. This is fun to talk about. People always like to get, it's a thing now to get granite countertops for your kitchen or whatever. There's a lot of radiation that comes out of stone because obviously there are radioactive products that are still inside that stone. So it's one of those ironic things that, you know, the environmentalist is completely anti-nuclear, but then has granite countertops put in their house because they don't realize that the granite's naturally radioactive and will irradiate them far more, and their food, far more than having a nuclear power plant 5 miles away. I just threw this sort of in as a history thing. German scientists Otto Hahn and Fritz Strassmann in 1938 accidentally discovered the process of nuclear fission. Lise Meitner and Otto Frisch explained the process and gave it the name nuclear fission. And so we've already discussed the stability thing a little bit, but what actually happens is you hit an atom, a nucleus, with a neutron, you cause that neutron to deform in the process, and when two halves of it get far enough apart, the electrical force becomes greater than the nuclear force binding the thing together as a glue, and they just split off into two. This is a typical reaction of what might go on inside a fission reactor. So you start with U-235, you hit it with a neutron, and it breaks into krypton and barium. And the thing that makes it work and the thing that makes it effective as a power source is when this thing breaks in half like this. Obviously, it's not strictly in half. One product's a lot bigger than the other. But when it breaks apart like this, it also tends to throw out 3 more neutrons, and that's what leads you to being able to make a chain reaction, because those excess neutrons can go off and hit other atoms and sustain the reaction. You know, if you got a big pile of this stuff, you can keep it going for a long time. But, you know, by a long time, I mean 25 or 30 years. Here's sort of the typical layout of a nuclear power plant, if you're not familiar. It's really a pretty simple thing. You've got a coolant that's circulated through this reactor core. You have moderators, usually cobalt rods or something like that, that go inside the nuclear material and can slow down some of these neutrons, capture some of these neutrons and slow the reaction down. So those are control rods that absorb neutrons. And the reactor core itself, which is nothing but a big pile of uranium. Okay, it's okay. It's more than, it's not nothing but, it's more than that, but you can certainly think of it that way. And so that coolant water is circulated. It goes through what's called a heat exchanger with other water. So the water inside the reactor never touches the water that goes to the steam generators. So ideally, no radiation ever escapes. Even if somehow the radiation from the pile leaches out into the water, that water doesn't touch the water that gets turned into steam. This water stays under pressure, which keeps it from turning into steam. That's run through a heat exchanger. That water gets turned into steam that runs a turbine. And so this thing is nothing but a big boiler. And then everything else is old technology. Works just like a coal plant or anything else. You boil the water, the boiler makes steam, the pressurized steam turns the turbine turns the generator, and you have electricity. So other as a heat source, a nuclear reactor doesn't behave a lot differently than any other power plant. So now we get into the reaction to nuclear power, even in the 60s. This is from a TED video made by Michael Schellenberger. I really like him. He's one of many environmentalists that we'll see in just a minute that started off as anti-nuclear. He was raised in a family that was anti-nuclear, You can think hippie if you want. If that makes you uncomfortable, you don't have to think that. But he was, let's say, he was raised by hippies. And so he started off very anti-nuclear. And when he started looking at it more closely, he realized that if you're truly an environmentalist, you probably have to be pro-nuclear, particularly with the problems that we're having now in this day and age with climate change, things like that. In this particular talk, he talks about the environmental movement back in the 60s and why they were so dead set against nuclear power. And some of the reasoning might disappoint you if you actually look into it. So here's a quote that he shares in his talk that I ganked from him, from Martin Litton, who was at the time was a Sierra Club board member. And he had flown over what's called Diablo Canyon, which was one of the places they built one of the first nuclear reactors in California. And he'd taken pictures of it. And, you know, they asked him about if he was concerned about nuclear accidents, nuclear waste, any of that stuff. And this was his response. I really don't care about possible nuclear accidents because there are way too many people anyway. I think that playing dirty, if you have a noble end, is fine. All right, so this is pretty infuriating to me as a scientist, because, and it's infuriating on a couple of levels, because this guy's telling you flat out that he really doesn't care about humans. So there is that branch of people on the planet that just see the human race as a cancer on the planet that should be eliminated anyway. Even though that might be arguably true, I don't think the destruction of the human race is something that I'm going to advocate for. And he thinks playing dirty is okay. Not everyone has our best interests at heart. To them, we're all useful idiots. Those people can be plant managers at 3 Mile Island, or they can be environmentalists. Be skeptical of everyone. That's me included. Don't take anything I'm telling you as gospel. I try to give you, sources, and if you want to call me and ask me for sources later, I'll certainly give them to you again. So do your own research. And the problem with that, of course, is we all have lives, and we all have jobs, and we can't research everything. But it's really disappointing to me how many people lie to you, even people that try to make you believe that they've got your best interest at heart. And they're not all just politicians. And they're not all nasty plant managers who are just trying to make a profit. Profit can be defined in a lot of ways. Gain can be defined in a lot of ways. So one of these things is not like the other. Here's a picture of a nuclear bomb exploding. It looks like an artist rendition to me, actually. But it's a picture of a nuclear bomb exploding in say, the Pacific Ocean, and a picture of a nuclear power plant. And so one of the things that the environmentalists have always done is they have tried to conflate nuclear weapons with nuclear power, and both things are very different. This is akin to saying you don't like chemistry because somebody made an explosive once, and explosives can be used to make weapons. Yes, nuclear power can be used to make weapons, but it can also be used to do things that are much more constructive for all of us. As a matter of fact, one of the things that I love to point out is that 20% of the power in the United States comes from nuclear energy. Half of that power, so 10% of all the power generated in the United States, comes from repurposed nuclear bombs. They've gotten the fuel from the former Soviet Union, mostly Ukraine, and they're repurposing those warheads into fuel for nuclear power plants. And about 10% of the energy that you get, depending on where you live in the country, comes from what used to be weapons that were aimed at you. Least you think I'm exaggerating. This film came out in the 90s. I'm sorry, in 1980. So they beat this drum for a solid 20 years. I'm not sure they ever stopped. Let me be abundantly clear here. This is dishonest. It's the kind of thing that leads to the polarization we now see in the political environment. It's why Democrats and Republicans are conservatives and liberals, however you want to put it, are always at each other's throats because they've all played games with the truth and nobody can have a reasonable discussion about anything anymore. And it starts with this kind of shit you see right here. Okay, I actually know they're still doing it. This is from another talk I give about junk science, and this was on Fukushima. And so here you have a magazine graphic that was put out. It says a radioactive nightmare. Okay. And it shows this scary looking plot with all these scary looking colors. And it's even got that subheading. As fallout from Fukushima heads our way, the government turns a blind eye. So to the uninitiated, you would believe that this map is radiation that's being spread from Fukushima into the Pacific Ocean. That graphic is wave heights of the tsunami. It has nothing to do with radiation or radioactivity. This was the plot of the wave heights of the tsunami that hit Fukushima and caused the problem in the first place. And nobody in Fukushima died from radiation or from the failure of the power plant. What are we talking about here? So this again is from the junk science talk, and you just can't ignore this graphic that somebody sent me. Remember the inspiring story about the Fukushima 50, the heroes who sacrificed themselves to clean up the nuclear plant disaster in Japan? Yeah, they're all fine. It's still true today. Exactly none of them have contracted radiation poisoning, and their long-term prognosis is good. A panel of experts found that the average cancer risk for the workers, not the people that lived in Fukushima around the plant, the people that actually signed up to do this job, the average cancer risk for the workers is 0.002% higher than the normal population. The accident wasn't nearly as dangerous as Chernobyl, despite the wildly exaggerated comparisons reported in the press. Yeah, and Chernobyl is one of those things that's completely indefensible. It was all human error, and it was all Russian Soviet irresponsibility that just can't be justified in any real way. So yeah, Chernobyl, it has been bad for the nuclear industry writ large, and there's not much we can say about that one other than it was a generation 1 reactor that should have never been online in the first place. Never, it should have been used for commercial power. So they want you to believe that there's a lot of material, radioactive material in the seawater in the Pacific Ocean because of Fukushima. Again, one of the other talks that I'm working on right now is called The Case for Math. People don't understand basic mathematics, and that leads to their detriment very often. So one of the figures that I read in an article was that 400 tons of radioactive seawater, tritium, by the way, which is not particularly that dangerous of a radioactive material, but 400 tons of it's getting dumped into the sea every day, and you go, okay, what does that mean? 400 tons of water is equivalent to 354 cubic meters, which is equivalent to that very small number, and it's 5% of Pacific after 1,000 days. So after 3 years, the amount of radioactive water that's gotten into the Pacific, thanks to the to Fukushima. And of course, this thing drops, this amount of pollution drops over time, but it's 5.36 times 10 to the minus 11%. So as a ratio, it's 10 to the minus 13. A millionth would be 10 to the minus 6. The billionth would be 10 to the minus 9. 10 to the minus 12 is a trillionth of the volume of the Pacific. And that's after 1,000 days of exposure. And tritium doesn't have a half-life of 1,000 days, by the way. So it's going to decay away and not be there to be at any volume higher than that. So here we have a list of pro-nuclear environmentalists. Stuart Brand is easily, I think, the most famous of all of them. I like the guy. I've seen him on some TED Talks. He has way more patience with some of these people on the other side than I do. But again, he started out as being anti-nuclear. Most of the people on this list have started out as anti-nuke. And when they did the research, they realized nuclear power was the way to go. You see Michael Schellenberger's on that list. I refer to his TED Talks a lot more than I do Stuart Brand's, but I do like Stuart Brand, and he is amazingly patient. That's the best thing I can say about him. He is a good guy, though. And I don't mind anybody trying to, get their arms around the stuff. Just don't lie about it, right? And so these guys have taken what I believe to be an honest look at the industry, and they're in favor of it, even though they've all basically been ousted by, Greenpeace or whoever they used to work for because of their change of opinion. So again, that's almost like a religious cult type mentality when you start expressing doubts about the standard model, of beliefs, and you just get thrown out of the organization. Not exactly the most objective way of looking at things, to say the least. If you just have to listen to actors and celebrities, here's a pro-nuke quote for you. It's like half the people who were saying no nukes are now realizing nuclear is the best way to go for energy for the future. I think it's natural to re-examine your beliefs as you age up. Interesting way to put it. I would just say grow up, but maybe he was trying to not hurt anybody's feelings. That's Robert Downey Jr. This fellow put out this statement. He is he's a science article writer and an environmentalist. He put out a statement right after Fukushima. The anti-nuclear movement, to which I once belonged, has misled the world about the impacts of radiation on human health. That is yeah. What's the word I'm looking for? Understatement. So here's the next problem, and this is specifically with renewables, because a whole lot of these environmentalists now are saying we can just skip the nuclear power part and go straight to renewables like wind and solar and that kind of thing. None of which I have a problem with, by the way, and I'll try to emphasize that a couple more times before we get to the end of the talk. This is called the duck graph. It's a little hard to understand exactly what's happening here. I always forget and have to go back and look it up myself. So I put notes in my talk so I wouldn't forget to tell you the important points. The duck curve refers to a graphical representation of electricity demand from the grid on days when solar energy production is high and demand on the grid is low. When plotted on a graph, the lines and curves form a distinct duck shape. So this is going to be California. I can promise you that. March 31st, so spring. And what you're looking at is the megawatts of power required by year. So there's what, 8 years worth of data in there. And you see that when the sun comes up, it's very mild weather in California. You see that when the sun comes up, the power requirements go down, which is exactly when you're generating a lot of solar power. So one of these ideas of renewables, solar power, it's great, but it tends to generate electricity at times when we need it the least. And the other problem is that the other plants can't just instantly turn on and off when the sun comes out or the wind decides to blow. I know that's very unreasonable of them, right? But it takes days for a nuclear power plant to ramp up. It takes half a day, a solid 3 hours to even ramp up a combined cycle plant that you've turned off because you say, oh, I don't need the power. And so then the afternoon comes, people come home from work, they start wanting to heat their houses and stay warm at night or whatever, turn on lights, watch TV. The power load increases, and it takes a good 3 or 4 hours to light the boilers and get these plants up and running again. So you have to, if you're in the power generation industry, you have to proactively know when to turn on all your old plants that just used to run 24/7 because all these renewables are suddenly giving you energy at all these not so optimal times. And don't even get me started on battery technology. If you think the current power generation systems aren't environmentally friendly, batteries have never been environmentally friendly. Yes, even the modern ones made out of lithium and all this other stuff. Those are rare earth metals that have to be, dug out of the ground, usually through strip mining. So no, they are not environmentally friendly at all. And when you start talking about storing terawatts of powers in battery farms, I don't understand why anybody would think that's a good way to go environmentally, quite honestly. So why fossil fuels? Here's your standard sort of chemical reaction that goes on inside burning methane and other hydrocarbons. Everybody understands oxidation. You see the products after the reactions have occurred. You get carbon dioxide. You tend to get a lot of water vapor too, but you get carbon dioxide. Nobody's too concerned about the water vapor that turns into rain or whatever and goes back into the water cycle of the planet. You generate a lot of carbon dioxide. The other thing that's important here, aside from maybe just having a passing understanding of the chemistry, is that you get about 50 megajoules per kilogram of fuel consumed. You don't have to know what a megajoule is. You don't have to know what a kilogram is. You just have to have that number in your head for comparison. Now here is a nuclear reaction. Neutron comes in, splits the U-235 atom, turns into krypton and barium, and 3 neutrons. That reaction releases 80,000 megajoules per kilogram of fuel. That's a lot. There's basically, just talking order of magnitude here, there's basically a factor of 1 million difference between a nuclear reaction versus a chemical reaction. That's part of what makes nuclear power scary, is because of the energy density involved. But this is the future, guys. I tell people all the time, if you walk around town with $1 in your pocket, you can't even buy a cup of coffee. If you walk around with $1 million in your pocket, you can buy any damn thing you want. And it's the same with power generation. This fuel, it takes a lot less fuel. It does a lot less environmental damage. And part of that is because of the energy density. Can you have an accident that's very spectacular because of this energy density? Well, let's not let's not misunderstand. You cannot have an atomic bomb from a nuclear power plant. But yeah, you can have some spectacular accidents like Chernobyl that can be very scary, but it's called progress. We tend to be scared of everything that's new and different until it just sort of becomes mundane and we're not scared of it anymore. Ask somebody from the 1800s to jump into a commercial airliner, go 500 miles an hour and hurtle through the sky and see what their reaction's going to be. Again, it's called progress. You've got to learn how to do this stuff and be comfortable with it. And the numbers bear that out. What's the safest and cleanest sources of energy? We'll talk about safety later, so focus on the right-hand side of the graph right now. People knock themselves out trying to figure out how much carbon dioxide is generated by each industry. And here's what we've got. You have 3 tons of carbon dioxide due to nuclear energy. And that is a presumably per year figure. And so where do you get 3 tons of carbon dioxide being generated from nuclear energy? All the environmentalists, all the other people that are answering to the environmentalists do everything they could to make these numbers as fair as they could. So this 3 tons of carbon dioxide come from digging the uranium out of the ground in the mines, building the plants, laying the concrete, that kind of thing. But once you have a plant up and running, you're not generating any carbon dioxide from a nuclear power plant, as opposed to 820 tons of it per gigawatt hour if you're talking about coal, or 720 tons of it per gigawatt hour if you're talking about oil. And you see, these other guys look a lot nicer. Wind 4 tons, solar 5 tons, hydropower 34 tons, all practically nothing compared to burning these fossil fuels. What about solar? I've got a calculation I'll show you here in a few more minutes. This was a discussion that turned into an argument on the internet. This was back in those bright heady days when I used to think I could talk sense to people on Facebook. So somebody posted this article about the new solar power plant they built out in the Mojave Desert and how great it was. And I just pointed out a few things that led to an argument. Now, I'm not going to read that whole discussion to you. You're happy to play this back and read it all if you want, but it made me sad because, again, it goes back to a basic lack of understanding of freaking math. If you don't understand math, that's fine, but trust the experts. If you don't trust the experts, then learn the math yourself and learn how to solve the problems for yourself. But you cannot not know the technology and the math and not trust the experts. Then you're just some idiot screaming in the wilderness and not doing anything good from doing it, unlike John the Baptist. So here we have a 377 milliwatt solar power plant. This is thermal solar. It heats up a solar furnace that, again, makes steam and drives a turbine. 377 milliwatts on 3,500 acres of land. A typical nuclear power plant, 1,800 milliwatts on 1,100 acres. Those 1,100 acres, by the way, are regulation required buffer zones. They tend to be almost like a state park, for the wildlife around them, right? Because nobody can live there. So they don't actually destroy the land in a nuclear power plant. Most of those 1,100 acres is just, natural land that the wildlife can live on. So you get 5 times as much power as above on 30% of the land. And that 5 times as much power is being generated night and day, rain or shine. So again, it's not that I hate renewables. I think people ought to knock themselves out, to make the renewables work as well as they possibly can going forward. But don't kid yourself into thinking that it's a solution that works today and can just be ramped up and work today. And again, I'll quote some more numbers for you in a few minutes to even drive that point home. So I highlighted one part of this discussion that I copied. Somebody says, I say, 377 is nice, 377 megawatts is nice, but that's a lot of land for 377 megawatts. Somebody says, oh, it's scalable. Oh, no, you don't know what you're talking about. So here's my last response. It's no doubt scalable. So the US requires about 20,000 terawatts of power, as best as I could tell. Some simple math means that we only need 53,000 plants like this one. And that's roughly 186 trillion acres of land. Given that the US has 2.3 billion acres of land, that's 81 times all the land in the US to try to go full solar for our energy requirements of today. And that's assuming the plants are able to run 100% of the time. So what's wrong with my math here? Again, I'm asking other people, what's wrong with my math here? Make your point, use the math. What am I getting wrong? How are we being screwed over by those evil energy companies? I'm good with alternate energy solutions. How long do I have to beat that drum? I just don't subscribe to the idea that it could all have been easily done 20 years ago if it wasn't for greed. This guy writes back and says, well, you forget solar panels on homes, so your numbers are way off and it's crazy. All right, that's a level of stupid that I just can't argue with, right? I'm telling the guy it's 81 times all the land that the United States has, and he says, well, you're not accounting for rooftops. This is somebody that just wants to have an argument, just wants to believe what they want to believe, and doesn't want to listen to the facts. And these are people that I no longer waste my time arguing with. And if you're one of those people and you don't like what I'm saying right now, feel free to not write me to talk to me about it. So here's your levelized cost of energy. It's a far bigger challenge than most realize, even scientists. There are solar plants in operation, but the actual power costs average around 35 cents per kilowatt hour. Now, very often I tend to think of cost as being a reflection as to how much effort you've got to put into something to get what you want out of it. 35 cents a kilowatt hour is 3.5 times higher than the national average. Coal, gas, nuclear, and hydro can all compete in the range of 8 to 12 cents per kilowatt hour. So who's ready to pay 4 times more for their electricity? So this is an old levelized cost of energy graph from Wikipedia, but I feel like the numbers are pretty factual and accurate. Levelized cost of energy is another one of those concepts where they take the cost of building the plant, the cost of maintaining the plant, the cost of the fuel. They try to take everything that's involved in whatever type of energy source you're talking about, add it up into a big total, and then divide it by the number of years that plant should be expected to be in operation. And so turn it into a number that fairly reflects the cost of whatever type of energy you're talking about. And you can see that some of this stuff is just not ready for prime time. Not unless we're willing to pay a hell of a lot more for our electricity than we used to be. I went back to Wikipedia to double check the numbers because that was from a talk I gave a couple of years ago, and they have changed the graph. And again, I fear that a lot of what's going on here is politics and not the actual truth anymore. But you see, there's a very different graph here from a number of different sources. It looks like 6 different sources. And nuclear still looks very favorably in terms of levelized cost for energy, except for the numbers calculated by one person in particular. And so here, we're back to political polarization. I don't know who this Lazard fellow is, but he's definitely an outlier. And he's probably just a liar too. But it's very disturbing to me as a scientist to see people play with numbers even to try to convince folks to do what they want them to do. And by the way, even this idea that natural gas costs 17.5 cents per kilowatt hour, yeah, okay, if you say so, but that's not, that's most of where we get our electricity from, and we don't pay that for electricity, and there's a profit margin built in. So I think what they're trying to build into these new figures is cost to the environment. But again, now you're in a whole nother type of argument. It's like, well, how do you decide what the cost to the environment is? We're talking cleanup costs. Are we talking about carbon credits and how they're calculated? Because that all depends on who calculates them and what they want to charge you for making a certain type of energy source. So here you see that one uranium pellet about an inch tall. And again, it's that factor of 1,000,000 in energy density, is equivalent to a ton of coal, or 120 gallons of oil, or 17,000 cubic feet of natural gas. The average U.S. household consumes 10,715 kilowatt hours per year. That's 4.4 tons of coal, or 4 of those pellets that you see right there. Very often the figure you hear calculated or quoted is that that's a household energy consumption. Your personal cost for nuclear power is 3 M&Ms worth of spent fuel per year. Physically that size of about 3 M&Ms. So this guy, Jason Stephan, is a big proponent of thorium. Thorium is fine. It's one of the ways that you can generate nuclear power. And we'll talk about why thorium is so great, at least in some people's minds, as opposed to uranium in a minute. But you see that little ball of thorium is equivalent to 1,000 train cars of coal. People get all bent out of shape about nuclear waste. What people miss, first of all, lots of nuclear waste can be put into a breeder reactor and used again. So it's arguable whether you really want to call it waste or not. But even if you do, this is waste that's not being thrown into the atmosphere and causing additional problems. One of the other things about waste is people will always tell you that all of the nuclear waste in the United States is equivalent to a football field and is about 50 feet deep. There are ash ponds from coal burning power plants that have more volume to them than that. And those ash ponds have broken free of their dams and flooded whole towns before and caused major evacuations. So even though nuclear waste should not be taken lightly, it is, again, that 6 orders of magnitude less than any other type of waste you generate in any other type of fossil fuel industry you want to talk about. So, yeah, it's dangerous, but don't pretend like it's a problem that can't be solved. There's multiple ways to solve this problem. And there's so much less of it to have to deal with that I don't care what you do with it. I don't care if you bury it in a concrete bunker that's 5 times bigger than the waste itself. It's still easier to get rid of and to responsibly get rid of than what we're doing today. Death rates from energy per production per terawatt hour. So again, you see that you've got brown coal. You lose about 33 people per terawatt hour just digging the coal out of the ground and burning it. 25 for coal, 18.5 for oil, 4.6 for biomass. This is all per terawatt hour. These are lives per terawatt hour. So if you like death rates per terawatt hour. Gas 2.82, so 3 people per terawatt hour. Nuclear 0.07. As much as we hear about the dangers of nuclear power, because of the fact that everybody's so scared of it and there's so many safety systems in place, it kills practically no one. We'll quickly talk about next generation reactors. One of the things that we're sort of caught up in this nuclear debate is just about all the reactors out there are light water reactors. They tend to run at about 275 degrees Celsius, and they were originally designed for ships. This goes back to the Atoms for Peace, Hyman Rickover, all of those days. And they were fine as a way to get nuclear power out there to various nations and stuff, using materials that weren't easily made into bombs. But there are so many Generation 3 and Generation 4 reactors that are better designs. They're not water cooled at all. So the whole problem of steam escaping, hydrogen bubbles like in 3 Mile Island that people are worried about, stuff like that, just aren't issues anymore. And they run hotter. And you say, well, why is that good that they run hotter? Well, it's basic thermodynamics that the hotter an engine runs, the more efficient it can be, at least potentially. And if you don't use it properly, then it may or may not be efficient. But the potential for efficiency is a lot better the hotter you run something. So there are modern day reactors, if we're ever allowed to build any of them en masse, that can achieve 50 or 65% efficiency because their operating temperatures are so much higher. And they're what's called walk-away safe. I've actually seen demos, particularly for a pebble bed reactor, but it works with the thorium too, where an operator can randomly turn all the dials and just walk away from the reactor and the thing just won't melt down. The pebble bed, I think, is the easiest to describe. The pebble bed is basically a bunch of billiard balls with uranium impregnated in them. And so they sit in this bed and they generate heat. But because they're not water cooled, you don't have to pump water through them or any of that kind of thing, they can never melt down. Even if they get as hot as they possibly can get, that ceramic that's holding the material together won't melt. And so you cannot have the kind of thing that most people are worried about, a meltdown, in the next generation of reactors. The thorium is a little different. The thorium salt, you do that with molten salt. They have a drain plug in the bottom that is, it's the same material. It's the thorium salt, so it has roughly the same melting point, but it's being refrigerated. It's got a refrigeration coil around it. So if the electricity fails and the refrigeration stops, that drain plug melts, and that molten thorium drains into a pan underneath the plant that spreads it out so that it can't go critical on you. So it's a plant that shuts itself down if there's some sort of disaster. There are lots of Generation 4 reactors of lots of different types. Pebble bed and the thorium are 2 of them. One major issue with nuclear power is the generation of long-lived radioactive waste. All right. The point of this graph is that if you start with thorium and you capture neutrons, you might end up with U-233, which is a much more unstable, if you will, form of uranium that decays very quickly and only has a 100-year half-life as opposed to a 1,000-year half-life or whatever. You can have byproducts or U-238 that makes plutonium or americium, which lives a lot longer. So a lot of the thorium proponents point out that the waste made by the thorium reactors is a lot less long-lived. What's ironic to me about that type of thing is that things with shorter half-lives tend to be much more bright, if you will, as far as how much intensity of radiation they give off. Things with longer half-lives aren't very bright. They don't give off a lot of radiation per kilogram. So seems like to me you're trading one problem for another, because you're so worried about the long-lived nuclear waste. But all of that is moot if you put the thing in a breeder reactor and you reuse the material. Another benefit of Generation 4 reactors is they're hot enough that their process heat can be used in aluminum, fertilizer, paper, and even some aspects of steel productions. These processes are also significant consumers of greenhouse gas emissions. So right now, with the way that all of our energy generation works, is all of these processes take the electricity that's generated somewhere else and run ovens with it. But a lot of this stuff can actually be made with the waste heat that's generated by these hotter reactors. There are other examples too, like most people don't realize that when you make concrete, you have to cure it, and that's a very energy intensive process. And a lot of people in different parts of the world could really benefit from desalinization of ocean water so that they can make drinkable water. And again, that's a very energy intensive thing. And you can use the waste products from these nuclear reactors, the heat waste, not any other types of waste. You can use the exhausted heat from these nuclear reactors to do some of that stuff and get some of that stuff for free. So I left my notes in just in case when I originally gave this talk. And I leave them here to make sure I make a few points before we wrap up. 1.2 billion people don't have electricity and they want it. So the third world's going to make power whether you want them to or not, and they're going to use whatever method you want them to or not. And we want them to because they're mostly burning dung to stay warm right now. And if you think the health effects of burning coal is bad, consider the health effects of burning dung in your fireplace in your own house. That's horrible. Nuclear power has averted 1.8 million deaths because of the fact that it doesn't pollute like coal. That's 370 times more lives saved than lost in the last 40 years. Now, here's the point about renewables that I want everyone to understand. In the past decade, renewable energy consumption is up 21 exajoules. You don't have to know what an exajoule is. It's just a unit of measurement. Renewable energy consumption is up 21 exajoules. It sounds very exciting. While overall energy consumption is up 51 exajoules in the last year. In the last year. So that's a decade compared to a year. China alone has added 30 gigawatts of coal-fired power, more than offsetting the 17 gigawatts that was retired worldwide. So we're still making more. If you're thinking worldwide, we're still making more coal burning plants than we're retiring. We're still needing a hell of a lot more electricity just in increases than what renewables are providing, even if you consider them as new plants, not taking anything else away. So it's a battle we're losing. Here I did some calculations. I always point out the 3 M&Ms as your personal cost. And somebody said, well, what's the cost, if you do turbines and whatnot, wind turbines or solar energy. And so for this talk, I wrote my answer for wind, and then I actually made us a table to show you how this stuff compares. So here you've got wind. If you live 100 years, given the capacity factor of wind turbines and whatnot, your personal share of garbage is about 2,274 pounds of, let's say 50% fiberglass, which is hard to get rid of. and then other things like, copper and concrete and steel. I threw hydro in there. I used Hoover Dam. Dams tend to vary wildly on their construction and how much power they put out. So I just had to pick one. I picked Hoover. That's 12,000 pounds of waste over 100 years. Now, dams are interesting in the sense that they have shared benefits. So I put a factor of 3 in there, just to be honest. Because, most people enjoy the lakes and recreation that come with them, and things like that. Water reservoir for fresh water. So there's 3 other things that you benefit from with the dam other than just electricity generation. So 12,000 pounds is a lot, but that's 3 cubic yards of concrete, basically. Solar thermal, like the plant in the desert we saw, that's about 4,000 pounds of waste that you'd have to personally be responsible for one way or another. Of course, you pay the bill and they take care of it for you, but you get it. If you're trying to be an environmentalist, this is the kind of thing I think you ought to look at. So you're personally responsible for about 4,000 pounds of waste over 100 years. And again, that's heavy metals and rare earth things that are not easily recycled. And then I've got that picture down there. Tried to do solar photovoltaic. It's hard to get numbers as far as mass and weight and stuff like that. So I had to end up picking one that was basically one you could put on your house, a personal one. But I still think, as far as photovoltaics work, I still think that's probably a good way to go to get an order of magnitude comparison in there on the waste. So those guys tend to live about 25 years before they have to be entirely replaced. It was about 500 pounds worth of stuff that would be good for about 20% of your personal requirements for electricity. None of these numbers are bad, mind you. They're just not as good as nuclear. Your personal share for nuclear is over 100 years, is basically a Coke can worth of nuclear material. You could bury that in a coffin with me if I had to take personal responsibility for it. And again, the same quote I've already read to you. Renewable energy is up 21 exajoules in the past decade, but overall energy consumptions are up 51 exajoules in the past year. So no, renewables aren't getting the job done. And this just in. Literally just saw this article as I was making this talk. The energy and nuclear waste could power the U.S. for 100 years. And that's the energy and nuclear waste, guys, the stuff everybody's worried about. But the technology was never commercialized because in the 60s and 70s, when they did this experiment and came to those conclusions, it wasn't considered to be as big of a deal and it wasn't considered cost effective. But Idaho National Labs has already proven this can be done and can be made to work. Takeaways. Here's what I personally think. Nuclear power is inevitable because the world needs it. Nuclear power is dangerous, but has a better track record than just about any other form of power generation. And that's using Generation 2 reactors. If we use Generation 4 reactors, I would expect it to be a lot better. Nuclear power is greener than other forms of power generation, period. Don't let anybody tell you differently. And yes, I do recall that I told you not to take my word for it either. So go find out for yourself, even though I say don't take anybody else's word for it. Don't take my word for it either. Nuclear power is cost effective and scalable. Most of what makes nuclear power expensive in certain areas is because of all the lawsuits and all the regulations that go along with building a plant. And we went a little over, but we're done. So hopefully you guys enjoyed that. Hopefully, whether you agree with me or not, you learned something from it. And thank you and have a good day. I'm going to go stop my recording now.